Hello, Adrian here from Sofeast. I'm hosting today, and Andrew Amirnovin joins me. Andrew, you've been on the podcast recently, so I'm sure listeners will recognize your voice, but thanks for being with me again. You are our reliability and new product development guru. Can we call you a guru? I think we can.
Sure, I'll take that. Thank you very much.
Okay.
Good to be here, Adrian, again. And this is going to be an interesting topic, I hope.
Yeah, so today we are going through test to failure. So test to failure in electronics, hardware engineering, if you want to give it its full title. So I suppose this again is another one of those topics that's related to product reliability, which is absolutely your wheelhouse. And for the listeners who are tuning in, what you're going to go through why test to failure is important, what is involved, why, if you are bringing new electromechanical products to market, in specifically, although test to failure can be used for lots of different kinds of products, as I'm sure you'll go into, this is one of the types of reliability testing that you're going to do on your product. So without further ado, stop number one in this episode is to just explain, what is test to failure?
Yeah, I mean, we're living in a world nowadays that electronics is pretty much part of us, right? We're carrying a mobile phone, a laptop, and sometimes there's some medical products and pacemakers, a whole bunch of stuff we're dealing with that basically they need to be reliable and they need to be durable. We need to be able to count on these equipment that we're using. And so, of course, it kind of poses all kinds of challenges for designing and manufacturing of these sorts of products. But one of the things that most, let's say, electronic companies are doing nowadays are making sure that they do some sort of test of failure for their hardware. And in fact, you could do similar for software as well. And then by doing this, you're really trying to find the limits of your product. And test of failure is not just hardware. I mean, you could do engineering. We're talking like electronics, voltage, and current test of failure, meaning you want to test something that you want to make sure it can handle certain excessive voltage, or excessive current. Like if the current jumps a little bit, for example, let's just say there was some thunder and lightning happening, and somehow a bit of electricity jump in your TV. You don't want your TV because of high voltage coming down all the way down the chimney to be able to burn so quickly,
Explode, yeah,
or even explode. So for that reason, a lot of companies are doing test or failure to make sure that the products can at least handle certain excessive conditions in terms of environmental risks, or in terms of risk of increase in current or voltage. So all of these are trying to be built into the product to make it slightly more rugged than just what the normal operating conditions would be.
So you're pushing the limits in order that when you finally make the product, you can be sure that the product will be able to cope with maybe use or conditions beyond what it will be normally in. So there's a bit of redundancy there.
Yeah, you said it right. So you're pushing, you're trying to achieve two objectives, really. One, you're pushing to the product to the limits to understand what the limit of the product is. For example, let's say you're designing the product to handle 100 volts. Well, if you don't test it beyond 100, you're not going to know. Is it going to fail at 100? Is it going to fail at 101, 102, 110, 115? What? So you need to push that so that you can say, oh, well, okay, it's really operating condition is 100 volts, but it can go up to 120. No problem, no failure. You see? So now you have
Mm.
20% roughly margin of failure. And that is the reliability. Basically, you have enough margin in there so that it's not going to quickly fail if the voltage was fluctuating between 100 and 110.
Yeah, okay. Yeah, that makes perfect sense. So that's sort of setting the scene. So we know why we're doing it. We know what it is. Why then? Let's go into a bit more detail. Why does tester failure matter so much to anyone that's actually developing and bringing a new product to market?
Well, it matters because in our daily lives, we're using so much electronics, we don't even know it. As I mentioned,
Mm.
smartphones, laptop, medical products, even, the cars that we're using. So
Oh yeah.
the reliability of these devices are really, really important to our lives, pretty much. I mean, if you're in a car and it breaks down, I mean, you basically your whole day is shot. If you have a mobile phone and all of a sudden doesn't work, boy, you're really gonna feel like, okay, I'm not gonna be able to be in touch with anybody. I have no internet, and what about all the files and photos, in there? So
Hmm.
they're all part of our lives now, and so for that reason, it is critical for these products to be reliable. And I think that I can at least think of 5 reasons why this is important. We need to be able to do test of failure to understand the weaknesses and identify the weaknesses that are in the design. It could be all kinds of related issues. It could be design, it could be materials, it could be components that we use on those.
Mm.
We need to understand where the weaknesses are by doing these tests, and we need to eliminate those weaknesses. We need to strengthen the components. We need to make the materials better so it can last to that limit of the test that we want, to the marginal reliability that we want. And number 2, I would say safety is one of the most important things. We want to make sure that if there was a fluctuation, like you talked about your TV exploding,
Mm.
what if the same thing goes for your mobile phone? Oh my God, people put that on their pockets right over the above their head, their heart, right on
Yeah.
that. I mean, imagine if this, battery explodes. I mean, it'll just shatter your heart. I mean, it is very,
Yeah.
very important for these things to be reliable and not create a dangerous and unsafe situation.
Mm.
So this is one of the reasons when you're doing test of failure, you want to make sure if it's battery, it's not gonna explode. If it is anything else, it's not gonna create a condition where it's unsafe.
Mm.
And then,
Okay.
of
Yeah.
course, from there we could go into quality control. I mean, in the manufacturing environment, if you do test a failure, it is really going to improve your production run. You're going to be able to understand how to test a product, because now that you know the limits, you can test the product within the operational limits, which it's going to be safe in the manufacturing environment, and it's going to be able to control the limits of the test. For example, if your voltages are fluctuating between 100 and 110, and you did the test of failure and you know that, okay, it's safe up to 130 volts, but in manufacturing, you have to test it for 100 and 110 because that's the operating conditions. And then you want to make sure
Mm.
that because you've done the test of failure, when the staff in manufacturing production line are doing these tests, they're not going to be injured. There's not going to be a manufacturing fire, So not only is safe for production, but also it keeps the production under control in terms of what you're trying to manufacture. So it follows certain standards, and basically it's just a good way of best in class manufacturing. It's a good way to do things. And then, of course, cost reduction is one of the most important things. If you know the limits of your products, then you can say, well, that's really too much durable, or there's no need for us to build a product that is going to be, for example, up to 200 volts, or it's going to last forever and never fail, right? So it gives you an idea of whether or not it's a product that is within the cost of your limits of your product, or maybe you designed this product and you realized, oh my God, it's actually failing earlier than what we expected. Once, for example, if it's on a hot conditions or cold conditions or certain environmental situation. And so that means that, okay, now you have to spend more money to make it more rugged, more durable. So it could be really going both ways. It could be in a situation, test of failure could be showing you a situation where you need to spend more money to make your product a little bit more durable. And the test of failure could also show you the results of the test of failure, could also show you that it's too much durable and there's no need to be so reliable, and I think that's all good for the customers.
And the cost of product returns, which you've written about before and spoken about for sure, and and fulfilling warranty claims and things like that. I mean, those costs are no joke once that starts happening.
For sure, that is one of the most important thing. Cost of returns is it can be hectic if you have a product that doesn't meet a certain design and or usability requirements, and for sure. This test of failure results, if done in right, and if they have been implemented in the whole design and development process, definitely could reduce the costs in the long run, and it could impact the field returns, meaning that you could have lower field returns and higher customer satisfaction because of knowing your product limit. And then, of course, the last part that I think is important is innovation. So when you're doing test of failure, honestly, you could run into situations where you could accidentally find products and components that could last forever and very durable. And you'll be like, oh my God, this thing unexpectedly is actually performing a lot better than I expected. Why? And then you get into it and you find out that the materials and or specifications used in that component and or material is actually exceeding your expectations. Probably is a discovery for your company that you could actually patent it. You could create better products and components or materials from that. So there are a lot of innovations happens when you're doodling with test of failure. I think there was this one guy that was doodling with certain materials, and he accidentally ran into a material that it can handle a lot of heat. And I saw a demo of that somewhere where he was torching an egg because he had covered the egg with this material. He was torching the egg and the egg wouldn't boil at all, wouldn't cook.
Interesting.
And I heard that they're using this sort of material underneath the space shuttle, so to prevent from any kind of a heat related issues when space shuttle is actually entering to the Earth atmosphere. So these are results of innovation because of somehow somebody was doing some test of failure and then accidentally ran into these kind of inventions.
If we go back to the weaknesses point, you mentioned that by pushing these limits, you're going to possibly find weaknesses in your, let's say, product that you might not see when it's being used normally, because of course we are looking at the limits here. I remember a while ago, you mentioned an example of, I think it was refrigerators in the US, where they were working fine in like the northern states and maybe like the Midwest and whatever. But as soon as you started putting them into like homes in Florida, they were failing. The motors or something in them were failing because the fridges were being forced to operate in a much hotter and more humid environment. And whoever had manufactured the fridge hadn't, well, they presumably hadn't tested for this and hadn't taken it into account, and it cost a lot in, warranty repairs.
Yeah, I kind of forgot the case study that we did on that one, but yes, you're right. It was a very reputable, important manufacturer those days. But this was right at the beginning, when there was not much understanding of how reliability is important to product. And so, yeah, exactly what happened, as you mentioned, they designed and manufactured these refrigerators, and it was working fine under normal, let's say, room temperature, and maybe even a little bit colder temperature was okay. But then when it was in hotter temperatures like Hawaii and humid temperatures like Florida, then it would stop. It would just, the motors will start burning. And way too many failures happening. And the company pretty much went almost bankrupt because of this issue. And I've actually myself experienced examples similar to that, where the company went pretty much almost out of business because every one of their power amplifiers were failing in the field, and they didn't know what was going on. And they lost almost 4 of their big customers. And there was only one customer left at the time. They asked me to come in and have a look and see if I can fix it. And then when I evaluated the product, I found out that most of these products they were developing used a certain fan to cool down the internal temperature of the product. And if the internal temperature was not cooled down to a certain operating temperature, the transistors would just basically fried because they were reaching really, really high temperatures. And so I wanted to understand why these fans were actually failing. I developed a test case for it, and we started testing these fans. And oh my golly, we noticed that when the fans reached about 52 and 53 degrees C, they would just basically stop and fail. And then I looked at their data sheet. I noticed that in the data sheet, it said max temperature 50 C. So it was understandable. We were running those fans beyond its operating condition, which was 50 C max. And so we talked to our designers and engineers, and they say, hey, did you know that you picked a part that is basically failing when the temperature is increased? And he said, well, no, I picked a fan that is going to be at least beyond room temperature. And I said, you see, what you don't understand is that the room temperature is okay, but inside these units, you have a lot of transistors running very, very hot. And if there's no fans inside, it could reach up to 70 C even.
Wow.
And it was very, very eye-opening for this design engineer. I think he was kind of a junior level. He was like, really? I said, yeah, come here, I'll show you. And he touched one of the heat sinks, and it almost burned his hand. And it was like, oh, wow, I had no idea. I said, yeah, so you picked a part that was basically not the right part. So he said, okay, what do you recommend? I said, well, you probably need to pick apart a fan that is going to be at least handling up to 65 or 70 C. And he said, well, how do I know that? I said, easy. So let's run this internal temperature and check it and see what's the max internal temperature without the fan running. He said, oh, good idea. And we checked it, and it was right on the dot, right about 65, 70 C. So we picked a fan that could go 70, 75 degrees C without failing. And then basically we fixed the problem, no more issues.
Interesting. But yeah, that does really illustrate it well. So yeah, that's a good one from your own experience. Cool. All right. So, I mean, at this point we know what test of failure is. We know why it matters in terms of the sort of benefits that you're going to get. And some may be a little bit unexpected, I suppose, like cost reduction and, driving more innovation when you're actually developing and designing products. But how at this point do we do this kind of testing? What sort of methodologies can we follow?
Yeah, that's a great question. So one simple methodology is just basically doing room temperature test and pushing the limits of your design. So that could be like voltage and current, just to see what happens. This will be like starting point. And you could do that on your bench test while you're designing your product. You could say, well, okay, everything is being all equal under room condition, room temperature condition. So let's see what happens if I push the current a little bit, beyond the limits of the operating condition. Well, let's see what happens if I push the voltage slightly higher than what it's supposed to be. And that could give you some indication of what kind of failures you could expect. The next thing to do is to run some kind of accelerated life testing. We call that ALT in reliability. And under higher temperature conditions and lower temperature conditions, and maybe even humidity, you want to know what happens to the product under test. And that is not even adding higher voltage or higher current. We're just talking about just what happens under those environmental conditions: higher temperatures, lower temperatures, and higher humidity conditions. And if you didn't find any issues, now you add other variables. Let's run that same test, but this time we increase or reduce the voltages and maybe critical voltages, and let's see what happens. And then what happens if no issues happen? And we're not talking about like excessively increasing the voltage. You could, although, but we're talking about increasing the voltage and current beyond what the operation condition would be. If the operating condition is 5 volts, and now you're pushing 5.5 and 6 volt, is that margin of reliability? Is it going to be okay? And all the tests that you're doing it on a reasonable hunch that this condition could happen. If the condition never happens, there's no need to test. But if there is a possibility that the voltage could increase slightly or could decrease under a certain environmental condition, then you must test for it. Okay? That's just one, right? ALT.
Great. Okay, so that's ALT, accelerated live testing. So what's next in terms of methodologies then?
Well, the next thing that you could do is high stress testing. This type of testing is mostly to check and see if any of your components, transistors, caps, resistors, active parts, passive parts, you kind of want to know if all of those are going to be okay under high stress environment. And high stress could be anything. It could be excessive voltage, excessive current. It could also be environmental conditions, like, for example, high temperature, low temperature, high humidity. You want to know if these high stress conditions could actually cause any kind of component damage or component failure. And that's really important because some of your components may not be able to handle certain amount of humidity or vibration or certain excessive voltage and current. And so you really need to know that. In fact, honestly, this is one of the most critical tests actually when it comes to aviation. Like you're building an airplane. You want to make sure that this airplane is coming down to like ground level, room temperatures, to ambient temperatures, like around 20 to 30 degree. But then what happens when this airplane goes way up to 50,000 or 30,000 feet? We're talking minus 50 degrees C at that level. It is so cold. And all kinds of things can fall apart at that level if your components can handle it. So yeah, these are definitely critical tests. Along the same line, of course, environmental testing, right? You want to make sure that, similar to that refrigerator example you talked about, if your product is going to be in extreme temperatures, extreme humidity conditions, vibration situation, like, during the transportation and shock, you want to make sure that your product has enough resilience and durability built in so it can handle real world situations. I remember I was a tourist in Amazon jungle, and I took a Sony SLR digital camera with me. Those days I was all about photography, and I took some great photos from the Amazon jungle. But when I was right in the middle of the jungle with the tour guide, it started getting extremely humid. It got to a point that the humidity actually got inside my electronics, and I couldn't turn on my digital camera anymore. It just failed. And for making sure that all the internal electronics doesn't fry, I took the battery out and I put my camera inside my clothes, my bag. And then when I got home, I used a hair dryer to dry it and let it outside in air conditioned and dry environment. And it took like 4 or 5 days or a week for this internal humidity, actually all the wetness inside, to dry and for my electronic camera to be able to come back and work. So,
you did rescue it though.
I did rescue. I was lucky.
Oh, that's pretty good.
Yeah, because those days I paid $1,000 for that.
Yeah.
But yeah, the environmental testing is extremely important when it comes to test of failure. And then there is the cyclical loading. This could be anything. This could be, for example, you're loading your product and unloading your product. You're testing your product under load, under no load, and this loading and unloading can actually make a big difference on your components. Some components can't handle the huge loading and unloading, or especially under stressful and conditions such as, for example, vibration and thermocycling. And if these conditions are not tested, they're going to be tested by the users eventually. And, because depending on what that product is, if that product normally needs to be tested for loading and unloading, and if you don't do that through test of failure, well, you're looking at all kinds of returns for that product for sure. And one of the important things that I have to say, Adrian, that a lot of companies might forget about it, is continuous monitoring of all the improvements that they have done. Basically, what happens usually is that something breaks and engineering comes in and does a fix on it, and the issue goes away. But most often everyone is so busy that nobody goes back and says, okay, well, we fixed this a month ago. Can we do some monitoring and see if there's any more failures coming in related to this failure that we had before? Is this fixed forever, or are we still seeing failures? And that monitoring is so important, because if you don't monitor, then you don't really know if the fix was effective or not. And so sometimes test of failure in those kind of situations will be another way of checking for monitoring, from monitoring point of view. And so you're pushing the product to see all those fixes actually made the product durable, and you're not seeing those issues that we're seeing before. And this is specifically good for, or especially good for, sensor type product, data acquisition type of product. but it really applies for all kinds, and I think it's very important to monitor your product when when it used to be a failure, but you want to check again.
I remember like a week or two ago, you were on the podcast with Renault and you were talking about the lessons learned database. Would you potentially add this sort of information into those sorts of databases? So whoever comes along next will see, what sort of reliability outcomings came from this testing.
Absolutely. Great point. I think that, all of these testing that you're doing, there are some lessons learned all the time. You're realizing that you tested it beyond certain capability, and either you learned something great about the product, like it's durable up to certain temperatures that nobody expected, or it's constantly failing before or prior to the operation limit. And that is not acceptable. So yeah, all of these information, lessons learned, goes into a lesson learned database. And when a similar product and or the next generation of that same product that is going to be an upgrade to what the existing product is very important for those same engineers or designers, especially new designers and new engineers. They need to understand what went on before and the history of that product before they actually upgrade the product.
Oh, yeah, absolutely. And I guess you might find a situation where you've got a part has been worked on, a component, and you find that it is still going to be absolutely fine for your new product or new version of the product as that it was for the past version that you're phasing out, because you found that it was durable up to well above and beyond what was needed, obviously within reason. So there's no reason to go out and source a new part. So whoever comes along and looks at the database, they're like, yep, okay, we can keep using that one.
Exactly. And you hit on it right there. So you want to make sure that everyone uses the lessons learned database as part of the normal process of the design.
Okay, so you've taken us through the methodologies that you're probably going to be using when you're doing test to failure. You've mentioned in passing some of the kinds of industries or products that you might be testing to failure. I mean, basically, anybody can use this particular methodology, test to failure, to learn about their products. But let's just go through quickly. I mean, just to make it very clear, the sorts of products and industries that this is typically going to be seen in.
Yeah, I think that this particular test to failure, is very common in aerospace, automotive, consumer electronics, medical devices, and industrial equipment. Definitely is very, very common in aerospace and automotive and consumer electronics and medical devices. And that covers all, right? So I know that if they don't do such a test, there would be a lot of major risks related to actually durability and reliability of that product. And aerospace, for example, you could have aircraft falling off the sky if there's a component failures. In automotive, there could be injuries. For example, remember the airbag that was not done right, and it was causing all kinds of people injuries. Consumer electronics, the same thing. It could be catching fires because of faulty battery. I think a good example will be the Note 7 that Samsung Note 7 that we talked about. Yeah.
Oh, Samsung are going to love us.
Right.
We always bring that one up in the podcast, but it is so true.
It is just one of those epic reliability failures that you just could not imagine, because people couldn't even get on the airplane because of that, and
absolutely.
Some people completely switched from Android to iPhone because of that. So it was just a very important thing. But yeah, I think those are the huge applications within the industries. But let's talk about some of the challenges that some of these companies could face. I mean, if
Yes.
you're talking about doing test of failure, for example, in automotive, let me just give you a picture. Let's say you're doing test of failure on a BMW, 7 Series. How much are
Hmm.
how much of those cars cost?
Oh, oh, I would guess. I don't know, maybe like $70,000, something like that.
Yeah, I mean up to 150 in US.
Oh yeah, yeah, yeah.
Yeah. So you're testing $100,000 car, and you're probably not gonna find all the issues with one test, and you probably
Mm,
can't do one test in one car. So you probably have to demolish and destroy up to 10 cars is very common, right?
mm,
So that's 10 times 100,000. That's about what, $1 million loss?
mm.
Right. That's just one product. But if you don't do it, then you're gonna pay a lot more if that product fails while someone gets injured, right?
Right.
So the amount of money you're gonna pay in liability and lawsuits and loss of good customers could be a lot more than a couple of millions. So
Mm,
so that's why they do that. And then
mm,
the challenges of how to do that. I mean, we're talking months and months of testing, having a very specialty environmental lab that can actually do these test of failures. And then,
mm.
of course, when you're done, what are you going to do with all those parts? You have to properly dispose of so that there are no environmental conditions. So, no environmental people coming after you. So that's just
Mm.
one industry. I mean, you could go to airspace, you could go to consumer electronics, and you run into all kinds of challenges. Um, just the fact that we're dealing with that. I mean, it could be safety hazard conditions, could be resource intensive conditions where a lot of people are working on one product, just trying to do
Mm.
test failure.
Okay. But this makes me think though, test to failure is quite a wasteful process. Now, before we start thinking, well, hang on, that sounds really bad. I think we have to put it into context, right? As you've mentioned with the example with, testing the BMW 7 Series, for example, right? Yes, you are destroying cars, and that means, maybe thousands and thousands of parts are going to go into waste, right? But if we consider, if you don't do this testing, you're going to have millions of cars being recalled. You're going to have to pull out lots of components from those. Those all get scrapped. Actually, the waste involved in that, you've got all of the emissions, the fuel to get cars back into the garage. You've got all the work that's got to be done, the scrapped parts. Then you've got to have new parts put onto them. All of this could have been avoided if you did the test to failure. So it's actually, although you are producing some waste, you are really preventing a lot more than you're going to produce.
Yeah, exactly. And I think the word waste is kind of negative word,
Sure.
and it kind of hides all the usefulness that comes out of this kind of a test. So
Mm,
I think that it's all useful. Useful is the right word, I think,
right.
because basically everything that you're doing on this test, it results in huge amount of exactly what you said, conservation in terms of product reliability, in terms of improvements in the environmental conditions. It really helps product to be more reliable and more durable, so it lasts long. And if it
Mm,
lasts long, then you'll own one product that you love, and instead of buying several products that after a while will die and you have to waste it and you have to throw
yep.
it away. And that itself is environmentally actually a green product when it's durable. So durability
Absolutely.
really improves the environment all.
Mm,
So yeah, I think if I had to conclude on this, I would say test of failure is critical in pretty much all kinds of electronics, hardware engineering. It's a task that pretty much every company should do to ensure reliability and safety of their product. And by subjecting the product and the components to extreme environmental conditions or an extreme electronics condition, like for example, increasing or pushing the limits of the voltage and current and trying to find the weaknesses in your product, all of these basically ends up being a better product and more durable, more reliable, and more cost-effective product, and really improves your design. So once you've done this, let's say once or twice, the next generation of the product, you probably don't need to do it anymore because you know limits and you know what components you're going to use. Yeah. So in the original product, it's a must, but in the upcoming generations, you may not have to do it. Doesn't hurt to do it, but you may not have to do it.
Interesting point. Yeah, that's really good. Okay, well, there you go. So that's taken us really neatly to the close, and that's test to failure. I've loved it. I think that's really helpful, Andrew. Thanks for coming on to go into that topic.
Absolutely, Adrian. Always nice to be here.
As ever, we will be back next week with another episode, and hopefully we will, of course, get Andrew along soon as well to join us on the pod. And we'll be back with you soon. Thanks again for listening to this podcast brought to you by the Sofeast Group. We're on a mission to provide you with everything you need to manufacture effectively in Asia, including inspections, auditing, new product development support, contract manufacturing, 3PL warehousing and fulfillment, and much, much more across Asia's key manufacturing areas. Visit us at sofeast.com. That's SOFEAST.com. to learn more and get help. If you've enjoyed the podcast today, please do rate, review and share because it will really help others discover us too.